Hi, this is Wollər Dynamics, and let's continue with our tutorial on the Ahmed body, the first tutorial. So far we have done geometry and some meshing. In this tutorial we're going to set up the case. So let's recall the geometry, what we have in the Ahmed body. This is a very well geometry test case. You will find a lot of information on the internet. So we have this geometry, and now we're going to set up this case. We need to set up the initial boundary condition and set the numerical scheme. So the first sense that at this point I hope you already have a mesh, and here just starting from a mesh. So remember, in the link you have there, you can download the case, so you will find these two files. Just follow the instructions there. We already have seen how to generate this mesh, so it's up to you. You can do the whole boundary layer in one step or in several steps, or if you don't want any boundary layer at all. So just follow here the instructions. In my case, I already generated the mesh, and actually have a quite good boundary layer meshing, as you see here. But this is my quartz mesh. As you see, we're not going to resolve very well the vorticity, but the case is okay, will run fine, and we are going to get some results that actually are close to what was bid. So this is our solution, and let me show you here. We have some streamlines, and you see that we capture the vorticity here, and actually in the wind tunnel cases here, you have the vortex detached, and then I have a clip plane here, and then you can see the vortices and the density. So this is a solution obtained using simple phone and a rather quartz mesh. It's very affordable, and this is the case that we're going to set up. And also we're going to do some post-processing basics, so we're going to compute some quantities such as this one, the Q criterion, which is a criterion used to capture vortices. You see here the isosurfaces represent vortices, and also we're going to compute on the surface the y plus, which is a very important quantity for when you're doing computations and using turbulence models. So in this case, and as you already know, so you're using wall functions, your y plus should be something between 13 and 400, and here we have it in our surface. So this will be our task. We're going to set up this case. So the first sense that after you have the mesh, and here we have it in paraview, you will see that as you start to inspect the boundary conditions, you will see here that the top, if I hide that one, you will see will correspond to an actual side wall. So this is not very intuitive. The left will be an inlet, so we're going to do some renaming. So let's skip this one, and when we do the mesh, we only need to if we are not satisfied with the naming convention that we have in paraview, that was in paraview, we can come here to the constant polymesh directory, and you open this file. This is the only file that you need to modify in this directory. The rest don't modify anything unless you know what you're doing, and here we just need to modify the names. So for instance, if we check in paraview, we'll see that top actually correspond to side. Let's call it side 2, that one. So I will do side 2 there, and something important that one will be also, we need to give a type to that one, and I know that one for me will be a symmetry. I don't symmetry in this case. It means that I don't have boundary layers as the condition. So be careful. Symmetry, you can only apply that boundary condition to planar walls. If you have a wall that is not planar, you will need to use the boundary condition, which are equivalent. So that includes keywords, or I can erase it safely, and be careful this information, do not touch this information. So now we see the left corresponds to, in my case, will be, I think, the inlet. Yes, so I will put here inlet, and that one, it is a patch. Patch means that can be any boundary condition. Newman did a slash. So I just need to assign in my zero folder the numerical value. The right would be the outlet. I know that is the opposite to left. And that one is a patch as well. Change as information. Erase this keyword underneath it. And let's see what is the bottom. Bottom in my case corresponds to side 1, I will call it. Side 2. Okay, now 1, 2. Okay, I erase this one. This will be as well symmetry. I don't want boundary layer there, so I will put symmetry. And let's see what is the front one. So the front one will be the top. Again, I don't want boundary layer there. Erase here, and back will be bottom, or probably I will call it ground. And that one also, I don't want boundary layer there. So this is a very idealized case. I don't have any boundary layer, just in the body. And the Ahmed body is a wall. Okay, I want to compute the wall shear stresses y plus I want to use wall functions there, so I need to define that one as a wall. So these are my naming convention, the type of boundary condition, and at this point we're ready to go. So as you check, you will have the 0 folder. In this one you already have the case preset up. So as you open, for instance, and compare to this one, you will see that we have the same naming convention. So in the inlet, I have inlet, it is a patch, so it can be any of the boundary conditions that I can use. So check the documentation, in this case a fixed value is entering. Then the outlet, I let the flow go out. Then I have a ground, so in this case I'm using a slip. Okay, so for instance, in this case not symmetry, I should put here patch. Okay, and then I have side. You see that I'm using wildcard, so sides are symmetry, the top is symmetry, and the Ahmed body is a wall. But as I don't have boundary condition, boundary layer, I fix my velocity value. So this is my standard setup. And just to point out again that slip would be equivalent to symmetry. So in this case, I just show a mixture of both. And again, as you keep checking boundary conditions, let's see what we have in P. So in P again, we have for the patch, or the patches what we define here, we can assign any of the numerical boundary conditions available, and the rest are this one constraining. So I have symmetry, symmetry. Okay, the ground in my case is still slip. And then we go to the other dictionaries that corresponds to the turbulence variables. So in this case, we're going to use the K omega turbulence model. So we need to define for K omega. And here we have inlet, outlet. Those are patches. We give inlet and outlet values. Then we define for the ground, the slip, the rest are constrained, symmetry, symmetry, and we have wall conditions, wall functions at the walls of the Ahmed body. Then we open omega, which is the other variable, and pretty similar. We have wall functions there. We use our boundary conditions, and then we set where our inlet and outlet. So the question is, how do we compute these initial values, this value that we give to the files? So usually it's a very good idea to read the theory, go find some papers or papers of the implementation, but you can come here in our website, and then you will have this thing, software and web tools, and here we have a calculator to estimate those variables. So if you enter here, and for instance in this case, if I will recall, my inlet velocity is 30 or 32, something like that. So yeah, 30. So you start here, you start to give your reference values. We'll put 30, and then I would like to compute K and omega using tools intensity and eddy viscosity ratio. In this case, I will set these two values to 1 and 1, and then I can press compute, and here we have the values. So this will correspond to my value of K or kappa and then omega, and as you check your dictionaries, kind of you will have values similar to those ones, as you see here. And then we can check also for omega, also we have our value. So I think those values I set it for 32, so let me check here. As I put here 32, okay, you see that here I have closer values, or maybe 33. So yeah, I ran this case using 33 the velocity. So as you check here, we have our value. So basically you go, there are some relations already established, original documentation, and you just compute those values and put it there. This case is that we're running with full wall functions. So after checking our boundary conditions, we keep exploring our directory structure. So then we go to constant, and constant we have these two dictionaries, plus we have the mesh, and we know what we have already in TreeSurface and this folder. So you open transfer properties here, you just basically set the viscosity and your transfer model. We're going to run using incompressible solver, simple fun and steady. And then in turbulence properties, you set up your turbulence model. So in our case, we're using the original K omega, the baseline K omega formulation, which use wall functions. So we set up our physics, and then we go to the system directory where we have our numerics plus the dictionaries related to meshing and some other utilities. So let's explore first the SVSkin, where we set up the numerical method to solve the governing equation. So if we open this one to see steady state, okay, we're going to use a solver called SimpleFun. Then we have the discretization of gradient, okay, and usually this is the way to go. There are some other methods, but this is a quite good method. So we're using this method, the Gauss method, to discretize all the gradients we have in the equation, plus we're using the emitters, okay. Then we go to the divergence, the convective part of the equations, and we're using a linear win for the divergence of view. And I have to say that probably 99% of the time you will use this method. This is a second order accurate method, non-oscillatory. It might become oscillatory in the presence of a strong radius. Then, so it's an advice that probably is a good idea to have 4 or 5 actions. So most of the time I use this one, but then you will have these other options that are a little bit more accurate, but a little bit also you get accuracy, but you're giving up some stability. Okay, so you have the UST, then you have the pure Gauss linear method, which is really accurate, but it's highly oscillatory in the presence of strong gradients. And then we have the win, that we know that this is the first order that will always give you a solution, but is highly diffuse. So advice, always run with this one. That is a good choice. Then we solve for the turbulence variables, K and omega in this case. And as you see here, we're using a win. To say before, the win is first order accurate, highly diffuse, but have in mind that we're using this one for the turbulence model. And turbulence, after all, turbulence is just diffusion. So using first order accuracy won't hurt much your solution, and it will promote diffusion and mixing. So I always like to use a win unless I'm using less than you need to go very, very high accuracy. And then you go Laplacians and grad scheme, which are related to highly related to how you solve the Laplacian, but also quality of the mesh. In this case, we have a good mesh, so limited one is a good option. And that's all. That is our discretization. And then we can open the SV solution. Here's how we solve the linear system. So for each variable that we're solving in our problem, we need to say give the convergence criteria. So you see that for P, U, K, omega, Phi also, we're going to show you phi because we're using initialization with a potential solver. So this is used for the potential solver, and these are the parameters related to the simple solver that we're using. We're doing 2 non-orthogonal correctors. I always like to do at least 1 non-orthogonal corrector. Okay, and I highly advise to do 2. It will be a little bit more time consuming, but you're getting more accuracy. And if you go and you compare with commercial software, most of the commercial software, they always do non-orthogonal correction, even if you have very good meshes. So it's a very good idea to do this thing. And then if you want, you can set up residual control. So if your residual fall below these values, your simulation will stop. And this is the number of non-orthogonal correctors that I will use for my potential solution. And then we have the relaxation factor that they're only used in a steady solver. So kind of this will control how fast our solution advances. If you don't know how to choose these values, I highly recommend you to choose the default values. And actually you will see that in literature, the default values are this one, P03, and the rest are 007. And here I'm using a little bit higher values. So the higher the values are, the faster your solution will advance, but you will give us stability. So the solution might become oscillatory. The lower these values are, so for instance, you put here 0.1, the more accurate your solution is, but your convergence will be really slow. So everything is about compromise. But here I'm using this relative high values because I'm using also another variant of the simple method. I'm using the consistent formulation. So I always also recommend you to use this formulation. It's more robust than the normal formulation, and you can get faster to the convergence as you can use higher on the relaxation factor. If you don't want to use the consistent formulation, just comment it or put no there, but remember that you will need to use a smaller relaxation factor. So at this point, that's all. I think the last dictionary that we need to check is the control dictionary, where we set just the running parameter. As you see here, running simple, we're going to run 1000 iterations. So this is the saving frequency, okay, and then I have it here some useful function objects. So you always like to print the minimum and maximum values. So here also can put node. So in each iteration I can see those values and see if something is going wrong. And also I'm computing forces. Okay, so I have my forces object, and also I'm computing the force coefficients. So I have my function object there for force coefficients, and I have the y plus also. So these are our dictionary, and pretty much I have to say that this is a standard dictionary for me. Probably I'm missing here the mass flow at inlets and outlets. In this case we don't need it, but in the next tutorial we're going to do a little bit more post-processing, so I will show you some other utilities, how to compute it after you have your solution. So that's all. At this point we're ready to go. Feel free, if you have your mesh, remember, read the instructions. I will close everything and I will show you how to run it. So we have everything. Let me erase this little folder. Okay, and I will copy my original solution into seeded. And remember that I told you that we're going to use an initialization method. Okay, we're not going to start from a uniform solution. So this is the solver that we use for that initialization. Should be here. So potential font. So you copy that line, put it here. So basically we're going to run a potential solver. We're going to compute a velocity field, and we're going to use this field as initial condition. So as we already have a very good initial condition, our convergence rate will be better. So the closer that initial solution is to your final solution, the faster you will converge. But yeah, you don't know that final solution, but this one is much better than starting from an initial field. So if I check here, see here that we have a velocity field, okay. And if you want also, you can compute a pressure field. You will do a projection of your velocity into your pressure by solving Bernoulli, but in this case I don't have it. I just want the pressure field, and this will be my initial condition. So we can run. As you type simple font, I will save the log file using T. Off you go. So we're running our Ahmed body, our mesh. I don't know what kind of mesh you have, and we're computing many things on the fly. So you see here that I like to print out these values, because also I like to see, for instance, if at one point you start to see crazy values here, you know that something is wrong. So you can or stop your simulation or go to your dictionaries, the numerics, and change something to stabilize your solution. So you can run in parallel, by the way, if you want. So I won't wait until the end of the simulation. I just want to show you that I already have some solutions here. So for instance, I will use this tool that probably you already know, Python, to plot my residuals. So I will use and I plot the residuals to show you my previous solution. So this is the behavior that I have previously. So see here my residuals. Okay, so we can say probably at about 300 we can stop. The solution is not changing anymore, and it's not stopping, it's not arriving to a convergent solution, because actually this is an unsteady problem. Okay, so my residuals will never fall below my criteria. So usually when you run steady solvers and they do not converge, that doesn't mean that the solution is wrong. That just telling you that your phenomena, whatever you're simulating, is highly unsteady, so probably it's better to change to unsteady solver. And what you have here is your continuity error. Remember that this has to be small. Okay, it doesn't matter if they are big or a positive or negative number, but they have to be small. Okay, the one that has to be small is the global one. Okay, which is this one. You see this is a kind of a small value, and the other one is the cumulative, is the summation of everything, so that one will increase in time. So we have there our residuals of our simulation. That was my previous simulation that I run in parallel, and also we can plot I also saved my forces. So for instance, say one I can plot the force coefficients. So let's go here and do some plotting. I already have prepare something here, I think. So for instance 1 3, so remember always your coefficients are saved here. Okay, force objects and force coil objects. So you go here, you will see this text file with all that information. Okay, so the first column will be moment, drag, and leave. Okay, so you have the information there, and actually you have this name because remember in your control dictionary you gave it that name to that object. So as you open here, you will see that my dictionary for force coefficient, I call it like this. So if you put something else there, you will have that name there. So we can plot that information that is in human readable format. So as you type like that. Okay, that wasn't using this line. So let me plot a little bit this one. Post processing, force. Okay, I'm plotting the wrong one, so force. Okay, I was plotting forces. So I was using 1 3, which is the drag coefficient. So as you don't know how to use plot, basically you just need to tell the location of the file. Do not forget the quotation marks, and then this means using column 1 and column 3 with lines. Okay, and this is the behavior that you have. Okay, and as you see, you can just click like this, and as you go to the literature, you find the paper, you will see that we're kind of in the ballpark of the drag coefficients the experimental ones. A few things that I want to tell you that, for instance, the geometry that we're using is a little bit off from the real one. So if you check the drawings, probably you will realize that the steels, now the support, I think that it is 1 or 2 millimeters shift from the actual value. We did it on purpose, okay, to get some a little bit different results. So now you can go and modify that geometry. You know that you have Onshape, highly parametrical, so you can change it quite easy. So check our drawings, go to the original drawings, and you will see that there is a difference in the steels in the support, but also the slant angle, the angle in the rear of this body. Okay, we're using an angle, if I would recall, 20 degrees. The actual papers, most of the paper will be 25, 35, 30 degrees. So the results won't be 100% accurate, but we're in the ballpark. Those are the results that we have. This case is not meant to be a proper validation case, just to keep things running. And at this point, you see that you have a very smooth solution. Everything is running. So I think this is all for the moment. Just run your case, wait until 1000, and then do all the post-processing. So just to note as well, after you have the solution, and as you were running up previous versions of OpenFOAM, probably 3 and 2, here in 4, post-processing is a little bit different. So for instance, if you would like to compute at the end of the solution, for instance, y plus value, previous version it was just y plus. Here you need to do something like that. Okay, so you need to say the solver, you say post process, you're going to do only post process. So this is kind of equivalent to the no flow XX function object, if I will recall. So you are just launching this function object. If you want to compute Wolৰীষ্টshear stresses, this is the way how you do it. And for instance, the Q criterion, you need to give the solver. Okay, this one just takes the velocity field to compute your velocity tensor, and as well for vorticity. So here you have a few guidelines how to do some post-processing, and then at the end just launch paraview and do your post-processing in the usual way. So let me open this case that I already ran to show you Q. So you have your solution, you will have all your values. Okay, you go to the last time step. Remember, here you have the time control, you are in the last time step, and here you can access that information. So for instance, if you want to plot Q criterion like isosurfaces, select here contour, okay, of what I want contour. So okay, give me a minute. First I need to enable those fields, select everything. I want to access that information, and I want to access that information in my mesh in the internal field. So you see that I have internal field. Okay, contours of what Q criterion, and then you give a value here. Usually Q criterion is a positive value, depending on what you're doing. Can be 10,000, 1,100. In this case, it's something about 100. So most of the time, it is between 100 and 10,000. So as you see here, we have those isosurfaces, okay, of constant value of Q criterion, which are not, okay, probably I need to okay, yes, I recall what it was. Yeah, I need to go because I mess around with the 1000 simulation, so I need to go to the previous one. So my 1000 solution is a wrong one. I was applying some other functions only. So as you see here, 1550, I use 100 there, and you see you capture here all those vortices. So these are the vertical structures, and well, you will see that here you will have those vortices. And you see here, this is, in reality, this should be a continuous vortex, but in this case, due to the mesh, that this is not the best mesh, but as you refine your mesh, you will see nicer, finer, more constructors. Obviously, computing time would increase. Okay, so I guess this is all in this tutorial. I hope this was helpful. And the next one, we're going to do a little bit more of post-processing, so we're going to go closer to the actual validation, and the final tutorial will be paraview. So thank you very much for your attention, and hope you enjoy. See you next time.